Lecture 8 covers sections 4.1 through 4.2.3. At the end of today's lecture, you should be able to determine the center of gravity of a body, the center of mass of a body, as well as the center of volume of a body using the method of disks and method of shells. For us to begin, let's talk about a body. Gravity, a body force, acts on an object uniformly throughout the whole body. And there exists a mass distribution in space when we consider a body. This mass distribution is going to have a single weight that is acting at our center of gravity. And we denote this by either point G or the center of gravity symbol. This weight is going to have a direction and a magnitude, and we denote this as W. Now, for us to determine the center of gravity of a body, we're going to isolate it from our systems. For example, we have a crane that's attached to a wall. We will remove that crane from the wall. And then we're going to pick a point on that body, and we're going to sum the moments about that point. For our body to be in equilibrium, the sum of our moments must be equal to 0. If we look at the figure to the right, we have delta W2 acting on R2, which is going to create a clockwise moment. Then we have delta W1 acting on R1, that's going to create a counterclockwise moment. Now, if we move G either to the left or the right, we can find the location where our sum of moments about G are going to be equal to 0. Now, we need a more robust method to determine the location of our center of gravity. And when we determine our x location, denoted as x bar, with respect to an arbitrary axis, we have the following formulation. X bar times the weight of our total body is going to be equal to the sum from I is equal to 1 to n of x sub I delta Wi, where our total weight of our body is equal to the sum from I is equal to 1 to n of delta Wi. We can see this on the figure to the left. Each weight is acting at a respective x location from our y-axis, and those weights are going to create a moment about said y-axis. Now, the figure to the right shows our total weight of the body acting at x bar. That is to say, when we take x bar times our weight, that is going to be producing one moment about our y-axis. Now, when we sum the product of x delta Wi, this has to be equal to our x bar location times our total weight of our body. Likewise, we can do this for the y direction to determine the y location of our center of gravity. And we denote this particular location as y bar. And y bar times the total weight of our body is equal to the sum from I is equal to 1 to n of y sub I delta Wi. And we can see this in the figure down below to the left. Now, delta W1 would have a value y1 above our x-axis, and delta W2 would have value y2 above our x-axis. Now, we see our total weight of our system, which is delta W1 plus delta W2, would be acting y bar above our x-axis. That is, we can take our moments about our x-axis and ensure that they're going to be equal, based upon the contribution of our body acting at y bar, and each of our members acting at their respective y locations. As the volume of our elements approaches 0, we're going to replace the summation convention and integration symbol. And we can define the first moments of the weight forces as follows. M sub yz is equal to x bar w, which is equal to the integral of x dw. M sub zx is equal to y bar w, which is equal to integral of y dw. And m sub x is equal to z bar w, which is equal to the integral of z dw. Thus, we can express a generalized formula for our centroidal location. That is, G, our center of gravity, is going to be equal to x bar, y bar, z bar, where x bar is equal to the integral of x dw per the integral of dw, y bar is equal to the integral of y dw per the integral of dw, and z bar is equal to the integral of z dw per the integral of dw.